Hey, how are you? My name is Lam Vu, and I'm with LITEON. So I would like to share with you a little bit about current share and Interop. Okay. Of course, it's a dream of all the system designer and with all the purchasing people that, if they can buy different power supply from different vendors and plug in the power shell and boom, they work together good, then everything is good, right? But there are quite a few differences that need to taken care of, right? EMI, right? Bandwidth, current share, so I would like to talk about one of those items, current share, okay? Everyone know how to do current share. The principle is very simple. Take the differences between the current and drive the voltage so that they can be equal. I mean, that is the principle, right? And everyone know how the circuit gonna look like, right? I mean, you can implement this circuit analog, or you can implement this same circuit as digital. There's no differences, right? I mean, the digital make it more flexible that you can change without changing the PCB, without changing the value, but the principle still be the same, right? So the principle is that each PSU will send out a signal to represent the current, right? And the signal is diode OR, so that the highest current will be the master, right? And the lower current will change the voltage so that it can match the master current, right? So the waveform is, I mean, the typical circuit is as shown on the screen. I mean, every design engineer knows this circuit. All right. So I would like to go back to the basic of the calculation, and from that basic calculation I can show you how you can define the parameter such a way that all the vendors can work together. Okay? So the basic is pretty simple. I mean, it's an op-amp. So I just wrote the equation of the op-amp, right? It has the positive input plus the differences between positive and negative input multiplied with the transfer function. I mean the gain, right? So it came out, so the adjustment is the master current, which is the positive input plus the error times the gain. All right. And when in the control system, when you apply this to a voltage regulation error M, the positive input is always constant. So when we do the small signal calculation, we basically ignore the master, the reference, okay? But unfortunately, in a current share, every time the slave change the current, the whole system change at the same time. So you cannot ignore this positive term anymore, right? All right, so how can we take care of that? Because every time you got a step load, the whole thing changes, right? So here, there's one more problem. I'm going to go back to the waveform, to the circuit to show you. In this circuit right here on the diode, the super diode circuit, this is a nightmare to the analog people, okay? This op-amp have to swing all the way to negative when the current is, when it's a master. And when it become it had to swing all the way to zero when it was a slave, and then it had to come back to normal when it is a master. So it's going to be a problem because, this have to swing so fast that it's difficult to make it stable, okay? And if you put some kind of capacitor on it, then your output current signal doesn't follow your actual current. And that's another problem, right? So that is the problem I'm described here, okay? So people usually have to put some kind of filter on the iShare signal. So if they do that, then, you know, if I calculate it out, then you can see that, you know, it came out the iShare, you know, become like a master current times the filter and blah, blah, blah. There's so many terms in here. But we don't want any of these things here. We only want to have this final equation down here as our principle. We said that differences in current drive the adjustment. That's all we want. We don't want all the other stuff. So how do we get rid of all the other stuff? Okay? Very fortunately that there is such a way to do that by matching the loop of the current share with the filter of the signal of the current share signal. What it means is that before you send out the iShare signal, you put it through a filter, okay? And if that filter is matching the loop of the slave unit, then you will see that all of this filter will cancel out and leave you with the equation that you want down here. All right, so let's go through it and see how does it look like, okay? So you see here now the iShare equal master current times the filter. This is the equation of the filter that right here. I mean, it's a voltage divider basically at frequency, okay? I wrote it as a voltage divider in terms of frequency, all right? And I use this term to put into the equation that I had before, okay? After go through all the algebra, blah, 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 that we already know since grade 9 or whatever, okay? Then the end of it, it will cancel each other, and then you will come up with the equation that have only the master current minus the slave current times the gain. The magic of this is for a power supply, you do not have access to master current. The master current is inside, go through a bunch of filter, so the iShare signal is not the true master current. But if you be able to match the filter internally with the control loop of the slave, then the end result is that you truly have the differences of the real current of the master versus the real current of the slave. Am I confusing you guys? You know, I mean, if you would like to, you know, come and ask me. I can send you the presentation. And once you have a chance to walk through these equations yourself, and then you can see that this is true, right? So once you go through this, then the solution is very easy. You know, the system designer can give out, say, hey, every power supply, you will need to make the current share signal have a certain filter with respect to the actual current. I mean, everybody can specify. If you specify that, and all the vendor will have their loop matching that filter, then your system will be stable. Okay? So the question is, you know, what is the range of the filter is reasonable, right? Is that 1 millisecond? Is that 5 milliseconds? Is that 10 milliseconds? I mean, what is it reasonable, okay? I mean, today everybody have a power supply. We know that. The crossover is about 1K. I mean, the best is like 2K. In some situation, maybe less, 500 hertz, okay? So let me say, if I dictate that, the filter has to be 5 milliseconds from the actual current to the iShare signal. The 5 millisecond is equivalent to about 32 hertz, okay? People say, what? Yeah, 5 millisecond, the time constant, 5 millisecond, that omega equal 1 over tau and frequency equal omega divided by 2 pi, right? So that become out about 30 something hertz. Okay, that is way lower than the response of the power supply. So every time the iShare make a change to the power supply have plenty of time to react to it, okay? I mean, so that is a reasonable number that you can specify. Okay, so how does it gonna work? So I'm do a little bit of simulation, okay? So I make it say, all right, I put two power supply, one with like 2K bandwidth, one with 1K bandwidth, so like 2x differences, okay? And using the same principle I just talked about before, I do a simulation. You can see that, well, it expected because one is much faster, so the initial current is swing way different down here, but then it swing here, but then it will settle to be equal, okay? If I use the two power supply with like similar bandwidth, say 1K, then you can see that the difference at the beginning is much smaller, and then they will swing back together, right? So, and this same principle that, with us with LITEON, there was some program that we work with other vendor to make them interop, then I applied the same principle. Then it came out pretty well. So that is basically all of my presentation today. So do you guys have any questions? If there's no question, if you want to do a little bit more detail, come to our booth. Give me your email, then I'm happy to send you the content.